So Scalasca is developed by Jülich Supercomputing Center. It has this notion that we can collect a very large amount of very low-level event trace data. This is something that various tools can do. But with Scalasca, we are focused on how to analyze this information, how to distill it down, how to present it in a more concise and high-level, insightful form. And we would like to present the information in the same sort of structured display with the 3 dimensions of having additional metrics, but with the context information of process and thread in the same browser which you were looking at earlier. By doing an automated analysis, we're guaranteed to cover the entire event trace and not miss things. It's often faster and more convenient than a visual trace analysis, but it relies on being able to do this in an efficient way to be able to execute the trace analysis in parallel. If we have to collect all the data together onto a single process, onto a single file, this is an unmanageable overhead when we try and scale things to many hundreds of thousands of processes. So in this case, we need a scalable parallel analysis. We can use a replay analysis where we actually use the same processes and threads that were used for the measurement to do the trace analysis. That will allow us to use the same partition, the same processors and memory that was available for the measurement. By having each of the replay processes replay part of the execution trace, exchange information with the other processes, we can have a very scalable trace analysis as a result. This was something that started off with the Kojak project in 1998. That was based on a serial trace analysis. Since then, we found the limitations of that as we had to work with larger machines and larger traces. So around 2006, we started the Scalasca project. When we got our first blue gene systems, that forced us to look into a parallel trace analysis, and that was done at the time with the local German research school. Our colleague Felix Wolf is now at the Technical University in Darmstadt. So Scalasca was developed with the focus of being a scalable performance analysis toolset supporting the most popular parallel programming paradigms, the MPI, OpenMP that you're familiar with. It's specifically targeted to very large-scale parallel applications, the sorts of applications you have running on K-Computer or on large Blue Gene and Cray systems, where we've been able to use Scalasca with up to 1.8 million processes and threads. These are very large configurations, very challenging configurations, but Scalasca has been able to handle these. The latest release is 2.2 that came out at the end of last year. As Christian said, we're working on a new release that should come out in the next month or so. But we already have support in here for the Intel Xeon Phi in native mode. There's support for efficient parallel trace handling using the CONLib format. And there's basic support also for analyzing measurements that include POSIX threads as well as OpenMP tasks. So it has a lot of the same characteristics as Scorpy itself. It's an open source BSD license. It's portable across a range of HPC systems. It's using now the Scorpy instrumentation and measurement infrastructure. That's, as we saw earlier, using OTF2 trace format and producing analysis reports in the latest Cube4 format. There's a number of limitations in things that we don't currently analyze, such as things coming from CUDA or for Shemem. Nested parallelism, I think, is also not yet supported. And things like the hardware counters aren't part of our trace analysis, even if they're recorded in the trace that is collected. This is the workflow for Scalasca. You've seen the part on the left-hand side using Scorpy already. So the source files get instrumented and combined with some measurement libraries at link time. This produces an instrumented executable, which when it runs means that each of the processes has the application which has been instrumented with our measurement library attached. That means that we can then do a default measurement so that we collect profile information on each process, on each thread, aggregate that information, collect it together at the end of measurement execution, and then show the results in the Cube browser, which you already saw. We can optimize the measurement configuration by doing some post-processing of this summary report, do some scoring of it to determine which parts of the measurement are interesting for us and which parts we can filter out. We also can add hardware counters into our summary analysis report and additional metrics if those are interesting as well. Beyond that, we can configure the measurement to collect event traces. That means that we'll have a buffer on each process where we're storing events. Those events then get written to the event traces at the end of measurement, or they'll get written to files during measurement if the buffers fill up. So that's something that's highly intrusive and something we would generally wish to avoid. But then these event traces, one for every process and thread, can then be analyzed in parallel using the same configuration of processes and threads as used for measurement here. And then at the end, we again aggregate the information, collect the information from each of the analysis processes to produce an augmented analysis report, which is which has these additional metrics that have information about wait states, waiting inefficiencies. This is an example of an inefficiency. So if we think of this as a timeline, time going from left to right, here we're seeing 4 processes. They're all calling a collective operation, MPI all reduce. The MPI all reduce cannot complete until the last of the processes initiates the call to the all reduce. So whatever was going on here was preventing this process from starting the all reduce until it got to here. And that means that the others have to essentially wait until they reach, until this last process is ready. So this is what we would call waiting time, wait at n by n in this case, waiting time on 3 of the ranks, waiting for the last of them in the collective operation to be ready to continue. This is an all reduce example, but the same applies to all gather and a number of other collective operations as listed there below. For something like a late broadcast, we can also distinguish things a little bit further. Here we have 4 processes executing a broadcast. This first process has to block here because it's waiting for the broadcast to be initiated by the root of the broadcast. Here, the second one in the list. At the point that the second rank initiates the broadcast, then this guy up at the top can start to expect the results to become available. Likewise, this third one will have to wait. However, this 4th rank here doesn't have to wait because the broadcast has already been initiated at that point. It can avoid having to wait for the root of the broadcast. Similar things happen if it's a scatter operation where there's data to come from one rank to be distributed to others. Those were collective operations, but we can also determine inefficiencies in point-to-point operations. The simplest example up on the left-hand side here is where we have blocking sends and receive. The send operation here at the top, the receive operation is blocking. The receive cannot complete until the send has been initiated. We don't know exactly the point where the send transfers the data. That happens inside MPI, but it won't start doing the send until you make the MPI call itself. So it won't start until this time here. So here we have the receiver initiating the blocking receive early. It has to block at least until the time when the corresponding send initiates, and we call this late sender time. There's a number of other variations on this when we're dealing with non-blocking communication. So here we have a non-blocking receive. The non-blocking receive allows us to potentially do some additional computation here, so there's no waiting time for that. The waiting time is when we actually wait for the results of the send. So whenever we go into the MPI wait call itself. Question?
Most MPI implementation have no progress span. It means that if the message is quite big enough, nothing will happen before MPI is sent, and the first time the progress span is called. So MPI wait, MPI test, or something else.
It can be the case that the communication is only initiated, actually takes place when it goes into the wait itself. At the moment, we can't tell what's happening inside MPI. MPI doesn't expose that information to us. There's ongoing developments in MPI and MPI 4, or is it 5, to provide some additional insight into what's happening inside the MPI implementation itself. And this would be interesting information to have, There were some proposals in the past, and some MPI implementations provided it, but it was never standardized. It was never widely available. It's something we're looking forward to seeing in future versions. Because we're working at the MPI level, we have something that's portable, but it doesn't tell you internally what's happening inside the MPI implementation, which of course can vary from implementation to implementation, can be controlled by environment variables depending on your eager limits and all sorts of other implementation-dependent things. We restrict our analysis to what we can tell portably from the MPI standard and how it defines these operations. So I don't think I need to go through all of the different variations. If they show up, you can refer to those. We're going to be using the Scalasca command. This is one command that you can use for almost everything from Scalasca. So if you just run it on its own, it will tell you the different options that it has. In the past, we had an instrument option where we could use our own measurement, our own instrumentation and measurement. Nowadays, you'll be using ScoreP. So this is only backwards compatibility here. What's a little bit more interesting are the analysis and examine options. The examine we already showed you that did some additional post-processing of the analysis reports to derive these additional metrics and provide some additional structure for them. There's a few other options here that are not so interesting, but basically this is just an entry point for using the other commands. The Scalasca instrumenter was abbreviated to SCIN. We can skip over that. Scalasca analysis can be abbreviated to SCAN, or you can Scalasca -analyze if you prefer the long version. We'll see an example of using that for controlling measurement. Internally, for the trace analysis, we'll be using a tool called Scout. Scout is our automatic trace analyzer. You can run it manually if you prefer, but one of the advantages of using this Scalasca analysis nexus is that it will automatically launch the trace analysis for you after the measurement is complete. There's some additional commands for synchronizing clocks between the different nodes. That can be an issue, especially on large distributed systems like K computer, also to a lesser extent on the Pi system. And the Scalasca examine command also has a shortcut, which is square working with reformatting and restructuring the cube files. What's the advantage of the scan command? It does a few things for you that are for your convenience. It sets a number of environment variables. It automatically exports those environment variables to the MPI processes. That's not something that's always done automatically. It is done here on the Pi system and on the K computer, but that's essentially non-scalable. So exporting your path and all your everything that's in your environment to all of the compute nodes is something that's inherently non-scalable, and you'll often find that large-scale measurements will fail as a result. So explicitly exporting the variables that ScoreP uses and Scalasca uses is one thing that's done automatically by the scan command. It automatically defines an experiment title or default name for your experiment. It provides a convenience for specifying filter files, etc. There's different ways of specifying things, as you saw on the command line or through environment variables, as well as things it determines automatically. It will also do some additional consistency checks as it's going through. So it checks that there's some instrumentation in the executable. It checks whether the directory that it's going to use is already available. If a directory already exists, it has the option of corrupting this for you. Sometimes that's nice, sometimes that's not so nice. But what it will do is instead block and tell you that the new measurement that you're trying to do is blocked by an existing one. Maybe this is one that you're already finished with and could delete. Maybe one that's still active that you actually want to keep. Either way, it won't overwrite or corrupt an existing experiment directory. And for the trace measurements, these is where the most important thing happens. After the trace collection is done, it will automatically launch the parallel trace analysis to start the trace analyzer, in this case the Scout application, running with the same number of processes, the same number of threads on the configuration, on the partition that was used to do the trace analysis. Bear in mind that nothing comes for free. This requires a little bit of extra time, so don't reduce your job script down to the basic minimum that's used for execution, or the basic minimum plus a little bit extra for ScoreP to write its analysis reports. or in this case, the additional trace files, but it needs additional time to actually launch and run the trace analysis as well. So you've already seen the initial steps of this process. We could go through it with Scalasca again, but I think we can skip that. We'll jump in the middle again and go a little bit further so that we show you first doing some summary collection with Scalasca, and then move on to the trace collection part. You already have things set up, so I'll just